Oh, hi there. Thanks so much for showing up for your math learning. It's Mr. Jennings. We're looking at the exponential functions formative test. We are going to go through all of the concepts here, so please check your work, and most importantly, check and build your understanding with this video. If you got stuck on a question and this video gets you unstuck, pause the video, complete the question, and then check your work after. It's a great way to build up your skills before the test. Here we've been asked to use exponent laws to simplify the following, and then giving answers as whole numbers or fractions with positive exponents, and no decimals are allowed. Supposed to not have any decimals. All right. First, one of our exponent laws is that 36 to the 1/2 is the same thing as the square root of 36. Minus 27 to the 1/3 is the same thing as the third root of 27. 6 to the 0 is the same thing as 1, and 3 to the -2 in the denominator is the same thing as 3 to the 2 in the numerator. This negative is a bossy landlord that just kicks the whole thing upstairs. Now we evaluate. The square root of 36 is 6, the cube root of 27 is 3, 1 is just 1, and 3 squared is 9. And if we add all this up, we get 13. This is 13. Very good. Okay, up here, we can recognize that -7 to the 2 is the same thing as 7 to the 2. Okay, when we square that -7, it's going to be positive. And we're going to raise that to the power 3. That's a kind of trick. This one's blue circle, to be honest. I made this one in a fit of rage, and it's blue circle. Okay. On the bottom, we have 7 to the 3 multiplied by 7 squared. We recognize 49 as a power of 7, so we can rewrite it and use our exponent laws, folks. It's amazing. Okay, then up here we have power to a power. So we multiply the exponents. 2 times 3 happens to be 6. Down here we have 2 powers multiplying one another, so we add the exponents. 3 plus 2 happens to be 5. Now we have 2 powers with the same base dividing one another, so we subtract the exponents. So we have 6 minus 5 is 1. That is just 7. Okay, show all that work for all the points, everybody. All right, let's carry on. Now, over here we have 6 over 5 to the -4. Oh, this is actually, I wish I would change this. It should be -3, because -4, who has that memorized? First thing that we would do is write this as 5 over 6 to the 4. The negative exponent just kicks everything downstairs upstairs, and everything upstairs downstairs. And then we recognize that this is 5 to the 4 divided by 6 to the 4. Okay, and then we have to work those out. So 5 to the 4 is the same thing as 5 times 5 times 5 times 5, which is equal to 25 times 25, which is equal to 625, if you didn't know. And then 6 to the 4 is the same thing as 36 times 36, which is equal to 900 plus 360 plus 36, which is equal to 1296. Right, I knew that. There, done. Okay, so that's how you do that one. This you might do on a calculator. I mean, do it on a calculator. But definitely be able to show that step, that you know like how to raise a fraction to an exponent, and you know how to work with this negative exponent there. Okay, 64 to the 1/6 is equal to, where's my computer? There it is, the 6th root of 64. Geez, I wonder how we could do that. Well, did you know that 64 is equal to 2 to the 6? So this could be written as the 6th root of 2 to the 6, but those are inverse operations. This is just 2. And our fact family is 2 to the 6 is 64, and 64 to the 1/6 is 2. So that's your answer. All right, those are the green circles. This one is very clearly blue square. Okay, all right. next are some blue square questions. So this one here, we've got negative exponent, so we're going to kick that downstairs. So we're going to have 1 over 81 to the 5/4, all right? Which is the same thing as saying 1 over 81 to the 1/4 raised to the power 5. Okay, that's how I deal with these and how I've shown you. Okay, the fourth root of 81 is 3, so we have 1 over 3 to the 5. Pardon me, I should have warned you. Oh, it's gross, disgusting. And then 3 to the 5 happens to be 243. So this is 1 over 243. Done, final answer. All right, now what about this mess? Well, in this case, all right, we have been asked to simplify and give our answer with positive exponents when possible. We are dividing powers with the same base. We have this is equal to 2 to the power 2/3 minus 1/2. Oh my goodness, how do we do 2/3 minus 1/2? Well, we are going to convert that to 4/6 minus 3/6. Okay, that's the same thing as 2/3 minus 1/2. And then we find that that's 1/6. So we have at the end of the day, this is 2 to the power 1/6. And we were asked to give our answers as positive numbers with positive exponents, and that is, if we evaluate it, positive integer exponents. Okay, well that has to change. Positive exponents. Good to try it, right? And that would be our final answer. If we evaluate that as not a integer. Okay, let's keep going. This one here is a black diamond because it has just all the things. First, we're going to do the negative exponent. So that flips the fraction, basically. To the 3/4. Also split that apart, so that's like 81 to the 1/4 over 16 to the 1/4, all to the 3. Okay, and then 81 to the 1/4, we've been here before, that's 3 to the 3 on top, over 16 to the 1/4, that's 2 to the 3, and that just equals 27 on 8. Done, final answer. Okay, we just do these. 3 cubed is 27, 2 cubed is 8. Here, the fourth root of 81 is 3. You know, these are things that your calculator can tell you. If you're using a calculator to get down there, that's fine, so long as you know how to explain your knowledge and explain your ability to evaluate those things. Okay, let's look at this one over here. This one is quite clearly black diamond. So let's zoom in, get lots of space, and really make my computer lag for some reason. All right, on the top, we are going to have 7 to the power 3/2 plus 4/5. Oh my goodness, we have to add fractions. All right, divided by 1/49. Well, that's the same thing as 1/7 squared. Look at that, I can create a common base again, raised to the power -3/20. Okay, in these cases, we will multiply those exponents, right? So let's do the fraction addition first. So we have, let's just do that in another color as a bit of rough work on the side. 3/2 plus 4/5. Here we multiply top and bottom by 5. Here we multiply top and bottom by 2. So that gives us 15/10 plus 8/10. That's 15. That's 8/10 in both cases. So together that's 23/10. Cool. Cool. So let's write that way. That's our numerator. Okay, so that's equal to 7 to to the 23 on 10. That's disgusting, but it is what it is. On the bottom we have 1 over 7 to the, we have to multiply these exponents. So let's do 2 multiplied by negative 3 on 20. That's equal to, oh gosh, am I going to do it this way? Yes, negative 6 on 20 equals negative 3 on 10. Okay, so there's our exponent. So that's to the negative 3 on 10. But that negative exponent just kicks it upstairs, right? So we have 7 to the 23 on 10 over 7 to the 3 on 10. And in these cases, we subtract the exponents. Oh my goodness, that's so convenient. We have 7 to the 20 on 10 minus 3 on 10. We subtract the exponents. So that gives us 7 to the 20 on 10. 20 on 10 is just the same thing as 2. So this is 7 squared. So this is equal to 49, which apparently was my favorite number when I made this test. All right, just hang with me for a second. Okay, let's keep going. All right, let's keep going. So we are now going to just demonstrate our exponent laws with these examples. Let's take a look. Oh, come on. What's sicker, my computer or me? Seems like my computer is sicker. You wouldn't believe how many times I've started this video for technical difficulties. But I appreciate you for hanging in with me. So this is 2, that's 6. We just multiply these. A cubed times a to the 1 is a to the 3 plus 1. We just add the exponents. B to the 4 is b to the 4. Okay, that's that. So this is 6a to the 4, b to the 4. Done. Over here, we raise everything to that exponent. Okay, so we have minus 2 squared. A to the 5 times 2, b to the 3 times 2, c to the 2 times 2. So that is also equal to 4. Positive 4, please. A to the 10. We're multiplying these. 4. Done. Why is that positive? Because the minus 2 is raised to the power 2. Minus 2 times minus 2 equals positive 4, please. Okay, let's keep going. This one is blue square here. Okay, otherwise they're pretty straightforward. This one here is, the first thing I might do is negative exponents, or we just work the inside. There's so many ways that you can take this apart, because it's all basically the same level of bedness. Let's do inside the brackets first. 3 times x to the minus 2 minus 7. We're going to minus these exponents. Y to the 4 minus 1. Okay, that's, where's that coming from? 4 minus 1? Well, this is y to the 1 down here, so we have to subtract those exponents. Okay, and all of that is still over 2 because we haven't dealt with that 2 yet. Okay, so now, and this is all still to the minus 2 because it was there, so it better stay there in your solution. Okay, don't just drop it because you forget that it's there. You want to deal with it later. Okay, so now we got 3x to the minus 9 y to the 3 over 2 all to the negative 2. Okay, next step will be to we're just gonna do that x to the minus 9, so I just got 3y cubed over 2x to the 9. Okay, that's a bossy landlord, and it sticks that whole bit down there. Just the x. That's the only thing being raised to the minus 9, not the 3, not nothing else. This is all to the minus 2. Okay, now let's do that negative 2 exponent. Okay, so we're first just going to do the negative over 3y cubed. All to the 2. Okay, see that bossy landlord? It just kicks everything downstairs upstairs and everything upstairs downstairs. Right? That's all it does. It just flips things. Okay, so let's keep it there in my notes. Don't need to erase it. And now we raise everything in there to the power 2. So that's going to be 4x to the 18 over 9 y to the 6. Why? Because we have 2 to the power 2. Here we multiply the exponents, so 9 times 2 is 18. Here we have 3 to the power 2, which is 9. And here we have 2 times 3, which is 6. That's our exponent there. So that's how that one gets evaluated. Okay, let's put our 2 back. 2. Okay, there, let's go. Okay, circle it. It's your final answer. You're very proud of it. Okay, circle this one too. All right, let's keep going. Oh man. Now, this one, I give you an equation and you tell me stuff about it, okay? So, when we're looking for y-intercepts or initial values, we can always just let x equal 0 and figure out what we get, all right? That's a strategy for any function because all along the y-axis, the value of x is 0, okay? So you can always just plug it in. But you can also remember that a, when you have y equals ab to the x, a is your y-intercept. That's your value there. So the y-intercept is a equals 3. Or you just tell me 3 is your final answer, and that's good. What's the growth factor? Okay, so here the growth factor is the number being raised to the exponent. It is the number b. So the growth factor is 0.4 equals b is the growth factor. And that's not growth, that's decay. It is decreasing. It's decreasing because than 1. It's less than 100%, so it's going to go down. A sketch would look like this. It starts up here at 3 and goes down pretty quickly and approaches 0 and then goes along 0 really close and then goes up that way. And this sketch can help us with the domain and range. The domain is x is all real numbers. We can literally put any value in for x along here and there's going to be a y value. The range is y is always greater than 0. Okay? Y is always greater than 0. It's never going to be down there. It's just going to approach and go down. And if you really want, you can use Desmos and explore that as a blue square topic to be thinking about the domain and range here. We didn't do that very much, did we? Okay, so we would say y is of the reals and y is greater than 0 and put that in curly brackets. And that would score you all the points. Okay, next, we are going to be given some functions. And we have to say, are these linear, quadratic, exponential, or otherwise? This one here, well, it looks exponential. Not really trying to fool anyone there. It starts low and only grows in one direction, just grows. It doesn't do this, which is go down to a vertex and come up. So there's our vertex. We've got descending and we've got decreasing and increasing ranges and things, or domains and things. And because it goes down and comes up. That's all we're really looking for at this stage. Okay, if we see that and it goes through a vertex, I mean there's a root there, right? It's quadratic. Okay. Now what about this function down here? Y equals 17 minus 0.2x. This could be rewritten as y equals negative 0.2 x plus 17, which you'll recognize as a y equals mx plus b, which is linear. Okay, there's an x, there's no exponent. Whenever you've got that, you've got yourself a linear relation. Now, what about this next one? $5,000 multiplied by 0.2 raised to the power x over 2? Wait, we're dividing x by 2. No, don't get confused. X is the exponent. Therefore, this is an exponential function. All right, let's keep going. Okay, if you can look at a table of values and tell me what type of function it is, that's a black diamond skill. Okay, here's how we do these. I analyzed the first differences here. I see this went down by 0.5. I see this went up by 0.5. I see this went up by 1.5. Oof. I see this goes up by, wait, 2.5. There it is. 2.5. Okay, I see this goes up by 3.5. And I see this goes up by 4.5. So cool. All right, so that's how much it's increasing between each one of those values. Those are what's called the first differences. Then we analyze the second differences. That got bigger by 1. 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 And that got bigger by 1. And when you see second differences constant, and non-zero, it's quadratic. Cool. So that's actually a review, and that's how you tell if a table of values is quadratic. And if you graph this, you'll see it goes down and comes up. There's 7, 7.5, 7, and so on, or minus, and then up there like that. Now how about this one? If we did the same thing, we would find that that grew by 1.6, and this grew by, gosh, what is it, 4.8, and then I see the pattern. This is going to be 4.4, right? And then it's like, oh, that's weird. Okay, well, let's check the, I can keep going if you want. This one is going to grow by, this is 0.2, 3, 4, 432, and then this one grows by, it grows to 4, so what is that? Gosh, well, you're all using your calculators, right? So let me just use mine. So I get out my calculator. I got my trusty calculator to do my first and second differences here. Holy, this computer maybe needs to go see the doctor. Yeah. Okay, so I go 194.4 minus 64.8, and I get 129.6. And I'm not sure that I'm seeing a pattern yet. Okay, so maybe I analyze them this way, and I find that this is 3.2, and I find that this is 9.6, and I find that this is, gosh, I don't know. Check the calculator. 43.2 minus 14.4 equals 288. Of course it is. Yeah. And then this one is going to be, oh, I can't do the math in my head. Yeah, I can. That's going to be 0.4, 6 is there, and then that's going to be 8. Right? Yep. Okay. And then I'm like, well, those weren't constant and non-zero. But then I notice, oh my goodness, look at this. If I just multiply that by 3, and then I multiply that by 3, and then I multiply that by 3, this one is not growing by addition. This one is growing by multiplication. And how can we find that? How can we investigate that as little investigators? Well, we just do 19.4 divided by 64.8. Okay, we just divide two adjacent ones and see that it's 3. And that's not enough to prove it, so we check some more. 7.2 divided by 2.4 equals this. And then we go 0.8 divided by 2.4, and we get 1/3. And we're like, oh yeah, we just divided in the wrong way. Okay, so we're multiplying by 3 each time. The other cool thing is, notice these are multiplying by 3 each time. And these are multiplying by 3 each time. If you do first and second differences, you'll still see the multiply by 3 pattern in there. Very cool, isn't it? It's so cool. Oh man, it's so bad. I apologize. This is gross to have on a video, but hey, we all got places to be, things to do. Okay, let's go. All right, now we're looking at mescalina. Okay, this is green stuff. To start, there we're gonna go black diamond with this idea. Okay, her morning coffee contains 200 grams of caffeine, and the amount of caffeine decreases to half the previous amount every 3 hours. Okay, so it's going to be 100 after 3 hours, 50 after 66 hours, 25 here, and 12.5 is half of 25. Draw a graph. Don't mind if I do, because I love me some graphs. Boom. 3 is 100. Boom. 6 is 50. Just put your points on there. 25. And 12 is half of 25, so that's about there. And then we draw the beautiful exponential curve. I don't know, I think maybe exponentials are my favorite looking curve. A little low there. Ooh, that one didn't go very well, but it's not bad. Okay, and then this is my function. Right, there we go. Does this situation represent exponential growth or decay? It represents exponential decay. Explain. Don't mind if I do. Well, oops, no, she's... That's a fulsome explanation of why it represents exponential growth and decay. So it's a domain and range. Okay, so here we would say x is of the real numbers, and we would also say that's it. Actually, x can be any real number, but really we're only concerned with x is greater than or equal to 0. Okay, and how am I going to do greater than or equal to? I'm just going to do that. Okay, so it's greater than or equal to 0, and then finish my tilde. Okay, so there's my domain. Why do I say x is greater than or equal to 0? We can start at 0, but we can't really like go into the before time. There wasn't caffeine there. She drank it. And actually, to be honest, it would look more like as she absorbed and then sort of join there. Probably the absorption curve is pretty fast for caffeine, but you know, this is math class, not nursing or medicine. Okay, but then we want the y values, and so y is also of the real numbers. Oh, what? The b numbers. What is that? Y is of the reals. and 200 is the biggest. That's greater than or equal to y, which is always greater than 0. As some of us noted in class, does that mean that there's always some caffeine in your body? Yeah, but pretty soon this is like just one molecule of caffeine or something that's like a pesky little molecule we can't get rid of. And it's out that way towards infinity. It never quite gets to 0, practically. Okay, let's write an equation to represent this situation. Yes, this is green circle. You need this skill. Everyone needs this skill. Should be able to say, well, y represents the amount of caffeine in her body. I was going to say blood, but I don't know if that's where it is. X represents time. Time since consuming coffee. Okay, these are important statements. They tell us what our x and our y's mean. And then we're going to say A, in this case, equals 200 milligrams. Our B is 0.5. We're halving it. And our H is 3. It's our half-life. So we use this function. Y equals A, B to the x on H. Okay, and instead of B, we often write 0.5. So then we have y is equal to 200 multiplied by 0.5, or 1 on 2, raised to the power x on 3. And that is our function. Cool. Use your equation to determine the amount of caffeine remaining after 8 hours. Okay, fine. That would be y equals 200 multiplied by 0.5 raised to the power 8 on 3 equals, we just crunch that on a calculator. Clear. But we don't crunch blindly, folks. We're 8 hours here. So we have a graph. We're expecting just above 25. Like if it were 30, we'd be a little surprised that it was that high based on this graph. Well, it was a little low there, but I'm thinking 28 based on this graph. Let's find out what we get when we crunch it on a calculator. Where's my calculator? Come on. Come on, computer. You know you want to do math for the students. Okay, here. 200 multiplied by 0.5 raised to the power. Please put your powers in brackets. 8 divided by 3. End your brackets. That's your exponent. Push equals for triumphantly. It's even higher than the 30. I'm so amazed. It's 31.5. I should have rounding instructions here. So pretend I said to the nearest tenth of a gram, tenth of a milligram. Okay? Because rounding to the nearest tenth means give me the tenths place. And if we look at this here, it's got 0.498 blah blah blah. Even if I ask you to round to the nearest hundredths, it's still 31.5. So it's a very accurate type of rounding there. Okay, let's keep going. Ooh, Miss Galina. She likes to take a nap when her caffeine level reaches 75 milligrams. Let's see, if she drank her coffee at 8:15 a.m., when should she go for a nap? To the nearest minute. Look at that. Rounding instructions there. That's good. Good, Mr. Jennings. Bad Mr. Jennings over here not giving the students rounding instructions. Okay, so you may find tomorrow that there's rounding instructions there for you. Okay, so if we go up here and we're looking for 75, what we're saying is, where is that going to be 75? And it really looks like 4.5, or like four and a half or something like that hours. but we want really accurate. So what friend do we all have that could give us some really accurate visualizations of this? Desmos graphing calculator. Let's go. So type in your function. Y is equal to 200 multiplied by 0.5 and the bracket, raise it to the power x divided by 3. There's our function. There it is in all its beauty. What? I can't see it, Mr. Jennings. Well, get your axes right. Okay, so there we go. Now we can see the part of this function that we need, and we just go in and we say y equals 75. That is the precise time, 4.24, okay, when her caffeine levels will be right. 4.24. Raise your hands if 4.24 means to you 4 hours and 24 minutes. Okay, I'm sorry, I did you dirty. It doesn't mean that. It means 4 1/4 hours. Okay, what do I mean? The 0.24511 there, we have to multiply that by 60 to get the number of minutes. Okay, there's 60 minutes in an hour, and this is just ever so slightly underneath a quarter of an hour. Therefore 14.7 minutes. But I asked you to the nearest minute. So that is to say 4.24 hours, or 4 hours and 15 minutes is the time we're looking for. 4 hours and 15 minutes, okay? So she drank her coffee at 8:15, all right? And we want to add 4 hours, 15 minutes. Well, that would be at 12:30. Isn't that a beautiful time to take a nap? 12:30? Oh, that's a lovely time to take a nap. So we should say Mrs. Gaulina should go for a nap at 12:30. PM. This was given in AM. And the sentence, beautiful. Now, Miss Galina's partner, she's a computer scientist, and she would like to convert this caffeine function, which was y equals 200 multiplied by 0.5 raised to the power x on 3. She would like to convert that to a function of this form, where there's no fractional exponent. Find the function for her. Okay, no problem. All right, this is a black diamond, and it's just this easy. Watch this. Y is equal to 200 multiplied by 0.5 raised to the 1/3 raised to the x. We just bust this up. Bust it up. All right, and once we busted it up, that's just a number. We just evaluate that on a calculator. It's so nice. 0.5 raised to the power, put it in brackets, 1 divided by 3 in the bracket. There's your growth factor, 0.7937. So this should have rounding instructions as well. Find this functions for her with all numbers rounded to 4 decimal places. If necessary. Oh, bad Mr. Jennings. Give the students rounding instructions. And also don't blow your nose in the middle of your video, you barbarian. Oh my goodness. I question my life choices. Alright, so now we know that this is y equals 200 multiplied by 0.79833, was it? I don't think so. 7937, not even, well, who cares? 7937 to the x. That is our function. Okay, so we are very pleased. We are done that question. Okay, this function has the advantage of just being able to take x as the number of hours, and this tells you that her caffeine goes down by about a little, like pretty darn close to 21% every hour, or exactly 50% every 3 hours. Okay, and that's done. Ooh, wow, what happened? Here we go. The value V of a car depreciates by 18% every year. Okay, why is this relationship exponential? The car is decreasing by a ratio every year, losing 18% of its value year after year. Okay, that is decaying exponentially. That's a fulsome explanation of what's going on there. Using the information, create an equation to represent the value of the car V. Well, we have this is A, and this gives us B. Okay, but it gives us B this way. B is equal to 100% minus the amount that it's losing. Okay, this is equal to 82%, which is the same thing as 0.82. So there's our B value, there's our A value, that's our function. Why? Oh, why did I use Y? This one specifically tells me to use V. V equals 24,000 multiplied by 0.82 to the power x, where x is time. X equals number. Use your equation to find the value of the car. V equals 204,000 times 0.82 to the 6 is crunch it on a calculator. Times 0.82 raised to the power 6 equals to the nearest cent 7296.16. Dollars. This is my life. All right. So let's go. We've got the population in 2009, approximately 6.8 billion people. The population is growing by 1.3. So this is our A value. A, okay. This is our B value is equal to 1 plus 0.013, which is equal to 1.0. Notice that is 101.3%. Okay, I've already moved the decimal place there, so you can just build them this way as decimals right from the start. Don't have to do them like percent like I did in the last problem. Okay, so that's how we build our growth factor. Always has to have that 1 in it, that 100%. Let's write an equation for it. So population, P equals population, okay? We'll say lowercase t is number of years since 2009. So we have P is equal to 6.8. This is population in billions, please. Okay, population is 606.8 multiplied by 1.013 raised to the power t time. There. How much will the population increase from there to there? Ooh, fancy blue square question, Mr. J. So here, population in the year 2020, well, that's t equals 11. Okay, this one is t equals 21. So I'm actually going to write that p is not the year, but the t value. 11 is equal to 6 times 1.013 to the 11. Okay, we're going to calculate this sort of a one-stop shop here. We're going to have p at 21. We're going to calculate that one as well. That's 6.8 multiplied by 1.013 times to the 21, sorry. And let's get our values from our calculator, cause gosh. Okay, 6.3 raised to the power, no need for brackets, 11 is just 11, equals, so 7,838. We're going to go to the nearest million, 7.838. Rounding instructions, Mr. J. Okay, I'll go back and fix all that. Don't you worry. Okay, 6.8, I know you're all very worried, times 1.013 raised to the power 21. There's going to be more people, that's my prediction. There are more people, 8.919. So this is the nearest million, because that's billions, and that's millions, and that's 100 millions, and that's 10 millions. Okay, that's how number works. All right. So now we want to find P21 minus P11. Okay, that's the difference. By how much will the population increase? So the difference in population will give us that increase. That is the same thing as 8.919 billion minus 7.838 billion. And that is this number minus 7.838 equals 1.081. Oops, no. There, that's a fulsome sentence answer. Okay, so now, suppose there's only enough fresh water to support 10 billion people. So this is to say, we want to know when is 10 equal to 6.8 to the t. We want to know what does t equal. And we know we have to go to grade 12 to solve for exponents, or we have to use Desmos or guess and check. But ain't nobody got time for guess and check these days. So we do Desmos. So we type our function into Desmos, okay? Boom, 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 go home. Boop. There we go. Here's our function. 6.8 we'll just do y equals 6.8 multiplied by 1.013 raised to the power x. And you might be thinking that's not exponential, but it is. Look at this. Look at the world's population going up to the 500 billions in the year 333. Only in 333 years will it be 500 billion. So that shows you some problems with this model, right? How can we support 500 billion people on this planet? Maybe you're going to find the answer to that. Now, we just want to know, when does y equal 10? Well, it's there. So 29.8 years, and this one has rounding instructions. This is to the nearest year. So the t is about 30, so we could say that t is approximately equal to 30 years. Okay, then we can say the water supply for our planet, our population, I should say, will become inadequate in about 30 years from 2009 or in 2039 according to this model. Okay, there. Beautiful. Good answer. Don't know what that is. All right. That's a good answer, but it's not a nice answer, is it? So I hope most of us are going to, see that year, and we're not going to see widespread dehydration or lack of sanitation or something like that. So let's think about what problems with this mathematical model might be. This is the last question, I promise. All right, so give two possible reasons other than mathematical inaccuracies why the above estimate may not be accurate. Okay, sure. So let's do that. Okay. So one problem is that this model may not follow actual population. Which may slow its growth when it approaches ceiling such as this water threshold. In the case, that is to say, like, as the population approaches something like 10 billion and the human population starts to feel the strain of a limited water supply, people may either deliberately choose to control the population and its rate of growth, or we might find that the rate of growth slows down as people begin to die due to lack of fresh water. This would suggest a practical limitation on the range of the function. i.e., for example, y is less than or equal to 10. Y can never exceed 10 because then we run out of fresh water. So the function might look like this, right? It would grow exponentially until it reaches 10, and then you're up against that water limit, right? That would be one situation. Okay. I don't need to talk about that. It's just it's just a way of my showing you that your limit is your creativity or your inventiveness or your ability to think about these things and make statements. They don't have to make a lot of sense. They just have to demonstrate your mathematical understanding. I don't believe that between now and the year 2039 that we're going to be doing things like harvesting water from where, like Europa or something. No, I don't think so. But if we did, it would certainly change things. Okay, last thing. Sketch an exponential function on the back page and turn it into something artistic. Don't mind if I do. I am on the skateboard. There. I'm going to go very fast until I slow down. Maybe a friend is like resting out here. And on their yeah, and they're watching. Okay, there you go. You can do better than me. All right, team. That's it for me. That is a lot of math. What time is it? Oh gosh, it's almost midnight. Well, it was worth it if it helps you learn. So I hope that video is useful to you and you can get ready for our evaluation and build these skills for the final exam and also for the study of money next unit. All right, can't wait, everybody. Looking forward to seeing your skills. Bye for now.